Hi guys, welcome. We're looking at week 6 and we're going lesson 94 for one day and then 95 and 96. So lesson 94, we're working with graphing pairs of inequalities on the number line. So again, we've graphed numbers on the number line. We know if it's greater than or less than. We use open circles if it's greater than or equal to or less than or equal to. We use the shaded circles. So if we're looking at a range of heights of professional basketball players, okay, we have a minimum and a maximum. So 65, including 65, all the way to 90. Okay, so we shade in those circles and then connect the dots because that shows our range of values of height of professional basketball players. So sometimes they'll run together, sometimes they'll run away, which we'll look at here in a second. So again, we can't just point it one way infinitely because that wouldn't be true. We don't have someone that's 120 inches tall, 10 feet. That doesn't exist. We don't have anyone that's 0 inches tall. That doesn't exist either. So we have a range. The height is greater than or equal to 65, and then the height is less than or equal to 90. So if we're looking here, use a number line graph and an inequality expression to describe the statement. The length of one side of a triangle is greater than 2 and less than 8. So side is going to go in the middle because we're saying it's greater than 2 and less than 8. Even we don't have a line below or greater than or less than, so there's open circles right there. It's 2, we couldn't put in 2 for S and satisfy it because 2 is not greater than 2. It's equal to 2, but not greater. We could put in 8 for S because 8 is equal to 8, but not less than 8. We use the open circles to indicate where we are in the number line. Okay, we can have sometimes where we have greater than or equal to and less than. They don't have to both be shaded circles or both be open circles. We can have one or the other. So if X is greater than or equal to -1, we use a shaded circle at -1. Okay, and then it's also less than 5, so it doesn't continue on infinitely. It's got to be less than 5 also. We use the open circle at 5 because 5 would not satisfy this inequality. -1, shaded circle to the open circle, 5. Times where they may be running in opposite directions. An example, we're looking at school officials. They cancel outdoor physical education classes when the outside temperature is below 40 degrees. And they don't want anyone getting sick or injured because it's so cold. But then also, if it's above 100 degrees, they'll close it, or not close the school, but cancel outdoor activities. So if T represents a temperature, we could write it like this. If the temperature is less than 40, or if the temperature is greater than 100, we would graph that on the number line. So we would have 40 open circle and going to the left. Obviously, if it's 30, 20, 10, 0, -10, -20, whatever, that's less than 40, so we're going to cancel. If it's 100, 105, 109, 110, 120, they're going to cancel outdoor activities for that as well. So these ones would continue on infinitely to the left and to the right, even though we know there's never been a day where it's been 5 million degrees or anything like that, or -2,000. It's still, for the sake of graphing, we use the arrow to indicate that it's going both directions. We use the word or to indicate that T must meet one or the other condition, not both. Therefore, graph is the union or combination of the graphs of each inequality. So we graphed one and then the other. They're not running together, they're running apart. It's got to meet one or the other. If it's 30, that's not greater than 100, but it's less than 40, so it meets one of the two. So we're going to close it. All right, we'll go over these inequalities in class when we return. And the next two lessons we're going to be looking at slant height of pyramids and cones. So we know pyramids and cones, unlike prisms triangular prism, cylinder, rectangular prisms, whatever it is, have the same shape top and bottom, whereas pyramids and cones come to a point. So the base at the bottom and the point at the top obviously are different. They're not congruent shapes. It comes to a point. So we have what's called the apex and the base, and then the slant height, instead of the height directly from the base to the apex, it's going to be the slant height that runs along the side right there. So if you have an ice cream cone and you measured from the circle at the top to the point at the bottom, then that would be your slant height. Or in a pyramid, if you go from the bottom of it, followed it up, the triangular face all the way to the top, that would be the slant height, shown right there. So pay attention. Again, all these dashed lines, sometimes it's hard to see what exactly is being represented when it's a three-dimensional shape. So we have our height of the actual three-dimensional shape runs from the apex directly to the base, and then the slant height, which runs over here. So don't get confused when we say height versus slant height. If we cut out a cross section right here, if we were to think of this as a cross section, if we were to take out a two-dimensional shape of this, or cut a plane through it or whatever, we would have this right here, and then over here to the base, and then up here. So what it would make, the base to the apex would be this line right here, showing right there, and then the distance over here, and then this bolded line right here, or the hypotenuse of this now right triangle, that would be the slant height. So we're going to use what we know about three-dimensional shapes and two-dimensional polygons to make a cross-section of this, so we'll have it in terms of a right angle and a right triangle, so we know how to work with it. The thing we got to pay attention to is now we're talking about a squared plus b squared equals c squared, and the base of a triangle versus the base of the pyramid, and we got to make sure we're not getting confused on what we're talking about. So if we have this cone right here, and the diameter is 10 centimeters, and the height of the cone is 12, so if we have this, we have the dash line around here to indicate that it's a circle down here. So the diameter is 10, so the radius is 5. Radius is 5, diameter is 10. The height, so from here, from the base to the apex is 12. We want to know what this slant height is. So again, we're going to think about this as a right triangle, because we're focusing in on this right here, this cross section. We'll draw it out right here. So what do we know? This is from the center to the side. That's one of our radius of the circle. So that's this distance right here. So 5. The height of our cone right here would be represented right here, 12. And then the slant height right here is what we're trying to find. I think our reference sheet uses this lowercase cursive L, so we can use whatever we want. So then we use what we know about right triangles and all sides. We know a squared plus b squared equals c squared, or I guess we're calling it L squared. So 25 plus 144 is 169. We take the square root. 13. So this is 13. So this distance right here, and we drew it off here separately, two-dimensionally, we're looking at the slant height right there. So once you kind of know what you're given and what you're looking for, you can set it up. Once you have it here, I'm confident you guys can figure out how to find the slant height, because it's just the hypotenuse of this cross section which makes a right triangle. Armin is building a model of the Great Pyramid to approximate proportions. The base of the pyramid will be a square that's 30 by 30. He wants the height of the pyramid to be 20 centimeters. What should be the slant height of the triangular faces? Sketch a net of the pyramid to model what Armin is building. Okay, so we draw it out. We know it's a 30 by 30 square. We were told that, and then we know that the height is 20, and then we can break this apart. We have a 30 by 30. We split that in half. 20 is our height right here of the pyramid. And so that, again, this isn't our face. This is looking at from the center to the apex. That's 20. So the slant height is obviously going to be more than that, because it's not going straight up and down. It's going at an angle, so it's going to be longer. We cut this in half. That means it's 15 on each side, so it's 30 for a base. So 15 squared plus 20 squared. That equals 625, and then we take the square root of that, and it's 25. So that's where we're getting this 25 from. So again, this is the cross section of the pyramid. Now this is the net of the pyramid. We have 30 by 30, okay? And then 25 was the slant height, so that's the distance along the face of the triangle. That's why it's right here. So this triangle and then this one related, but not the same thing. 30 by 30 and 25 by 25. So Armin should make the triangular faces of the pyramid using a slant height of 25. He needs to do that in order to get the dimensions and the proportions that he's going for. So this was kind of a wordy example of find the slant height of this pyramid. That's what we're doing. We know that it's a square at the base. We know the height of the pyramid, and in our cross section, that's the height of this triangle, but that's going to give us the slant height right here. So we have it in a right triangle. We use a squared plus b squared equals c squared. Okay, and then the last one for week 6 that we're going to be looking at is the geometric measures with radicals. Okay, so again, a radical, I don't know why the text, I think the book is, I don't know why the text in here is all weird and over itself, but again, in your book, I just checked, it should look normal. But a radical, again, root 2, that's an irrational number, so instead of writing it out or using a rounded decimal, we can just leave it as square root of 2. Use it as a radical. Now, what we can do with radicals, just like when we're adding 4 pi plus 2 pi plus 3 pi, or 4x plus 2x plus 9x, or whatever. When we're combining like terms, even though this is not an unknown, this is an actual value, it still has the same properties. If I have one of them, 2 of them, 3 of them, 4 of them, okay, I can do it as 4 root 2. That's the side length, 4 times the side length, and we would just leave it as that. And so if we're looking at this right here, and we have find A, the perimeter, and B, the area. So we would need to draw this out. Okay, plot our points, connect the dots. We have a rectangle right here. So we need to find these different side lengths. Okay, normally I just say count left or right, but they're not horizontal or vertical. So we're going to have to use with the Pythagorean theorem, which is the distance formula. So I'm over 1, 2, up 1, 2. So this is 2 squared plus 2 squared, which is 8. Okay? This square root of 8 really gives me 2 root 2. There's the square root of 8. So I went over 2, up 2. Here I went over 2, up 2, right there. So then define this distance, which is the hypotenuse of this triangle we're using, which is really the side length right here that we need to find. Okay, well, 2 squared plus 2 squared equals c squared. Well, this is 4. It's 4, which is 8. Take the square root, and then we can break this apart using the property we talked about of numbers under a radical. We could multiply these to get back here, or we can factor them out to get here. And we do that because the square root of 4 is 2 times the square root of 2. So that's what we're doing here. We would do the same thing here. Up 1, 2, 3 over 1, 2, 3. So 3 squared plus 3 squared is 18. Square root of 18 is square root of 9 times the square root of 2. Square root of 9 is 3. So that's where we get 3 root 2. So all of that to say, here's our rectangle. And now to find the area, so here's our rectangle. I know they have it kind of like this. This one is 2 root 2. It's 3 root 2. Now we want to find the perimeter. So I have 2 times the square root of 2. I have 3 right here, and 2 and 3. We just add them up. 2 plus 3 is 5. Plus 2 is 7. Plus 3 is 10. So I have 10 root 2 for the perimeter. Add it up all 4 sides. Now if it was 2 root 3 or something like that, we can't, because square root of 2 and square root of 3 would not be the same. We wouldn't be able to do that. But since it's the same radical, we can add them together, just like when we're combining like terms. 10 root 2. Now for area, we know it's length times width. So again, we can multiply. This is multiplication, this is multiplication. So we can multiply in any order. 2 times 3 is 6. Square root of 2 times the square root of 2 gives me the square root of 4, which we know is 2. 6 times 2, we get 12. And its area, so we call it 12 square units. All right, so if we're looking at this and we want to find the length of the hypotenuse, it's a 1 square root of 3. Square root of 3. We want to find our hypotenuse, and then we want to find the perimeter. So a squared plus b squared equals c squared. 1 times 1 is 1. Square root of 3 squared becomes just 3. So I get 4. Take the square root, c equals 2. And this is one of the 30, 60, 90 special right triangles that we talked about. And they have these ratios. So 1 to root 3 to 2. So the perimeter, 1 plus root 3 plus 2. Add these together, we get 3 plus root 3. And we just leave it as that. 3 plus root 3. We're not multiplying, so we can't call it 3 root 3. We just have to leave this 3 plus root 3. Obviously, if we were doing an actual, like, building a garden or pouring concrete or something, we'd probably want to get it to the nearest whatever and then round it off. But since we don't want to write out a bunch of decimals or round, we weren't told to do that, we're just going to leave it as 3 root 3. All right, that's all we have. Like and subscribe, question, wonder, always do all those things.